Alright, welcome to the pre-calculus review for Unit 3 on exponential and logarithmic equations. Starting with number 1, graph each of the functions. So we know that to graph it, we're going to want to make a table of values. So there's my inputs, and I'm going to use what we talked about in class, those 5. If we need more, we can always add more. And then I'm going to go over to my calculator, do Control+ to add a graph page. And I'm going to put in my function, negative 1/2 to the x power plus 3, and that's going to give us an idea of what the graph looks like. And then I'm going to do Control T to add a table, and I'm just going to use the table to fill in my values. So -2 gives me -1, -1 gives me 1, 0 is 2, 1 is 2.5, and 2 is 2.75. And when I plot each of those points, -2, -1, -1, 1, 0, 2, 1, 2.5, and 2, 2.75. So we have a graph. It looks like that. And if we keep looking at the table over here on the calculator, our outputs keep getting closer and closer to 3, but they never actually touch it. Because if we remember, a regular exponential function has a horizontal asymptote at 0, and this tells me that I'm shifted 3 units, so it would be at 3. So I have an asymptote at y equals 3. My domain, even though it looks like there's a vertical asymptote on the left-hand side, we know that the domain is all the x values. X can be anything we want, so our domain is truly -infinity to infinity. And my range we have from -infinity until +3. So moving on to number 2, we're going to do the same thing. We're going to make a table. Same inputs, -2, -1, 0, 1, and 2. I'm going to add a new graph. And this time I'm going to graph 2 raised to the x plus 1 minus 2. We get that picture. I'm going to look at my table. And once again, -2 is -1.5, -1, 0, 2, and 6. So -2 is -1.5, -1 is -1, 0, 0, 1, 2, 2, 6, and we have a graph that does this. And as we come down, again, we talk about the horizontal asymptote. We're shifted down 2 units, so we're going to have a horizontal asymptote at -2. So our graph should look like that. Asymptote y equals -2. Domain, again, is all real numbers, as it always will be for exponential functions. And my range is -2 till infinity. Looking at number 3, 3 and 4, we have logarithms. The way we did these in class was we actually graphed the inverse of that function and then plotted those points. So what we're going to do to get a better table is we're going to find the inverse of number 3 very quickly. So remember the rule for finding the inverse. You switch your x and your y. So we get x equals -log2 of x plus 3 plus 1. Solve to get, that should be y. Solve to get y by itself. So it's going to be x minus 1 equals -log2 of y plus 3. divide both sides by -1, so that's going to give me negative x plus 1 is equal to log 2 of y plus 3. I'm going to take each side to the second, exponentiate each side to cancel out these logs. So I get 2 to the negative x plus 1 equals y plus 3. Subtract the 3. So 2 to the negative x plus 1 minus 3 is equal to y. And now I can make a table for this. Remember the table. I'm going to go ahead and make the table for that. And while I'm doing that, remember that the inputs and outputs are switched for inverse functions. So we have about 2 to the negative x plus 1 minus 3. And the reason why we do this is just so we get better values for the table. Control T for my table. And when I look here, now if we look at our regular table of -2 through +2, this is what we would have for my the exponential function. From the inverse, which is the function we want to graph, the negative log 2 of x plus 3 plus 1, I'm going to reverse these. So I'm going to have an input of 5 and output of -2, 1, -1, -1, 0, -2, 1, and -2.5, 2. And the reason we do this is just so we have better values to graph. So 5, -2, 1, -1, -1, 0, -2, 1, and -2.5, 2. That puts me there. And for logarithmic functions, we have a vertical asymptote, and that's going to be at x equals -3. We're going to have this vertical line here. And so our graph is going to look like that. And there's no horizontal asymptote. So my domain is now x has to be between -3 and infinity, so just greater than -3. And my range is, since it's the inverse, my range is now all real numbers, -infinity to +infinity. Alright, now number 4, we're going to do the same way. So we're going to start by finding the inverse of our original function. Remember, we're graphing this original function, but we want to make the table based on its inverse. So we're going to start with x equals log 5 of y minus 2. We're going to go ahead and exponentiate both sides. So 5 to the x is equal to y minus 2. Add the 2. So 5 to the x plus 2 is equal to y. This is what we're going to make the table for. So I'm going to make a new graph page. I've got 5 to the x plus 2. There's my graph table, and once again, I know my outputs already are going to be -2, -1, 0, 1, 2, because those, I'm going to look at those inputs from the inverse function. So I get 2.04, 2.2, 3, 7, 27. So 2.04 is going to be -2. So 2.04, -2, it's about there. 2.2 is -1. It's going to be somewhere around there. 3 is 0. 7 is 1. And 27 is 2, so I'm not going to be able to do that. But I'm going to have, again, a vertical asymptote at right at +2, so that first dot that I made right here is actually just inside of it, but my graph is going to look something like that. So my vertical asymptote is at x equals 2. domain is 2 to infinity, and my range is negative infinity to positive infinity. Alright. 5, 6 are expanding and condensing. Remember our rules. Addition turns into multiplication and vice versa, and division turns into subtraction and vice versa, and exponents can become coefficients. So what I'm going to do first, I've got, if I'm going to expand this log, I've got multiplication on the top, division, and more multiplication on the bottom. So first thing I can do is break this up into the natural log of 7x squared minus the natural log of 5 times the cube root of x squared plus 7. And I can separate this into the natural log of 7 plus the natural log of x squared minus, separate this out, the natural log of 5 plus the natural log of the cube root of x squared plus 7. I want to make sure these stay grouped. And the last thing I can do is take care of my exponents and my radicals. So I've got the natural log of 7 plus 2 natural log of x minus the natural log of 5 plus 1/3, because remember a cube root is the same as the 1/3 power. 1/3 times the natural log of x squared plus 7. And that is my final answer for A. B, I'm going to start the same way. Let me change colors real quick. So again, I'm going to start by separating the top and the bottom. So that's the natural log of 3/5 root of x squared minus 1 minus the natural log of x to the 6th. And then I'm going to separate this out into the natural log of 3 plus the natural log of the 5th root of x squared minus 1 minus, I'm going to go ahead and move that 6 to the front, 6 natural log of 6 of x. Then I'm going to take care of that exponent on this guy, so it's the natural log of 3 plus 1/5 natural log of the x squared minus 1 minus 6 natural log of x. And that's my answer for B. 6, we're going to condense, so we're working the other way. Remember, addition is going to turn into multiplication. So let's see, let's start with combining these. I'm going to go ahead and move this 3 inside. We've got 1/3 times the natural log, I'm sorry, not the natural log, log base 2 of x plus 5 times x minus 2 cubed plus log 2 of the 5th root of x. Now since this 1/3 is wrapped around this entire log base 2 here, that means that I can have log 2 of the cube root of x plus 5 times x minus 2 cubed plus the natural log of the 5th root of x. And then I'm going to simplify this a little bit more. This cube root and this cube are going to cancel. So the only thing left in the cube root is 6 plus 5. And then I'm going to multiply all of this times the 5th root of x to make that one logarithm. So my final answer here is going to be log 2 of the cube root of x plus 5 times x minus 2 times the 5th root of x. And that's going to be my final solution for A. B, this time I have a subtraction sign in between, so I'm going to divide. So bring the 2 up front, so I've got the natural log of x minus 3 squared over, I'm going to multiply these since it's addition, so that's 1/2 natural log of x plus 3 times x. Simplify that a little bit more. That's the natural log of x minus 3 squared over the natural log of the square root of x plus 3 times x. And that's as far as we really need to go. 7. Find the y-intercept. Remember back from chapter 1, the y-intercept is when x is equal to 0. So we're just going to plug 0 in for each of these x's and solve. So y is equal to 4 to the 0 minus 3 plus 3. Plus 3. So y is equal to 4 to the negative third plus 3. So if we need to use our calculator, 4 to the negative third, so 1 over 64 plus 3. Remember, we would prefer exact answers that are simplified, which I did not do. So let me try that again. 1 over 64 plus 3. That's going to give me 193 over 64. So my y-intercept is 0, 193 over 64. B, same thing, plug in 0 for x. So y is equal to 3 to the 0 minus 2 plus 1. Y is equal to 3 to the negative second plus 1. That's going to be 1/9 plus 1, which is 10/9. So I have 0, 10/9. 8. X-intercept, that means y is equal to 0. So this time 0 is equal to 2 plus log base 2 of x plus 1. So negative 2 is equal to log base 2 of x plus 1. We're going to exponentiate both sides. So I get 2 to the negative second is 1/4 is equal to x plus 1. Subtract the 1. So x is equal to 1/4 minus 1, which is negative 3/4. So that gives me negative 3/4, 0. For b, 0 is equal to 2 minus log base 2 of x. Subtract the 2. Divide by negative 1. So 2 is equal to log 2 of x. Exponentiate both sides. So 4 is equal to x. So my x-intercept here is 4, 0. 9. Solve for x. Give answers to 3 decimal places. So solve for x, first thing we're going to do is divide by 14. So e to the 3x plus 2 is equal to 560 over 14, which is 40. We're going to take the natural log of both sides. So 3x plus 2 is equal to the natural log of 40. Subtract the 2. Divide by 3. Remember we talked about in class waiting until the last second to get your final answer. I'm not going to use the calculator until right now. So now I have the natural log of 40 minus 2 divided by 3, which gives me 0.563. Number 10, same thing, except for this time I have 2 logs. They have the same base with addition, so that means I can use my exponent rules for condensing, which says I can multiply those two together. So that leaves me with a single log, 10, of x times x minus 3, and that's equal to 1. I can exponentiate both sides. So I get x times x minus 3 is equal to 10, because it was 10 to the first power. So I get x squared minus 3x is equal to 10. Subtract the 10. equal to 0. That should factor to be x minus 5 times x plus 2. If you don't want to factor it, again, we can use the quadratic formula. And when we solve that, we get x equals 5 or negative 2. But remember, we have to check both of those. When we check them, we have to make sure that our logs are positive. So log base 10 of 5 is good. Log base 10 of 5 minus 3 is also good. But if I try to plug in the negative 2, the negative 2 will not work here. So negative 2 is extraneous. Moving on, more solving. So I'm going to divide by 250 for part B. E to the 0.02x is equal to 10,000 over 250, which is 40. Take the natural log of both sides. 0.02x is equal to the natural log of 40. Divide by 0.02. And we get 2,000. We can go ahead and do C. I'm going to stay on the left-hand side. I'm going to add 4 first. It's equal to 15. Divide by 2. So 3 to the 2x minus 5 is equal to 15 halves. I'm going to take log base 3 of both sides. So I get 2x minus 5 is equal to log 3 of 15 halves. Add 5. So 2x is equal to log 3 of 15 halves plus 5. And then I'm going to divide by 2. So this is what I'm going to plug into the calculator. And when I do that, I have log 3 of 15 halves plus 5 over 2. And I get 3.417. Remember, we want 3 decimal places. Alright, right hand side, B and C. So I have 3 logs, 1 on the left, 2 on the right. I'm going to use my condensing rules again. This time it's subtraction, so I'm going to divide. So log of x minus 1 is equal to log of x minus 2 over x plus 2. Since they have the same log base, I can essentially cancel them out. What I'm really doing is taking to the 10th, exponentiating both sides, and I get x minus 1 is equal to x minus 2 over x plus 2. And then I'm going to add 2, multiply by x plus 2, so those cancel. Expand the left side out, x squared plus x minus 2 is equal to x minus 2. Move everything over. These x's are going to cancel, these negative 2's are going to cancel, so x squared is equal to 0. That means x is equal to 0. And if we check it, 0 doesn't work here. It's not going to work here. So even though that was my answer, since there's nothing left, this one gets no solution. Alright, C. Again, we're going to condense the left-hand side. It's subtraction, so we're going to do some division. So we have log base 5 of 2x plus 1 over x minus 5, and that's equal to 2. You're going to exponentiate both sides by taking the base 5. So 2x plus 1 over x minus 5 is equal to 5 squared, which is 25. Multiply both sides by x minus 5. Those cancel. 2x plus 1 is equal to 25x minus 150. Nope, 125. get everything on one, let's see, get the x's on one side, get the numbers on the other. So we're going to have 126 is equal to 23x divided by 23. And that gives me 5.478. So x is equal to 5.478. That's my solution. It's definitely going to work here. And since 5.478 is larger than 5, this is also going to be positive, so it's going to work there as well. Alright, 11 and 12. Alright, for 11, in 2012, a certain continuously compounded savings account has 552.59 in it. In 2014, the same account has 610.70 in it. How much will they be in the account in 2019? So what we need to know, since it's continuously compounding, that's A equals P e to the RT. We need to know what the rate is. So if we treat 2012 like it's the initial year, and we treat 2014 like it's the final year, we can figure out the rate. So we know how much we have at the end, 610.70. That's equal to the amount that we had to start with, which was 552.59. E to the R times 2, because it was 2 years from 12 to 14. So we're going to solve for R. So we're going to divide both sides by 552.59. So 610.70 divided by 552.59 gives me 1.10516, and that's equal to e to the 2r. I'm going to take the natural log of both sides. So the natural log of 1.10516 is equal to 2r, and I'm going to divide by 2 to figure out what my r is. So I'm going to take the natural log of that answer that I just got, divide it by 2, and my rate is 0.049995, which is about 5%. But we're going to try to be as accurate as possible. So the question is, how much will be in the account in 2019? Well, that's 7 years after 2012, so I'm going to go back to my interest formula. I'm going to plug in 7 for t with my interest rate and find a. So I get a equals my initial 552.59 e to my 0.049995 times 7. Put that in the calculator. 59 e to the 7 times 0.049995, and I get 784.14 because we're running to the nearest penny. And if you round your R value a little bit, you're going to get a little bit different result. Just to show you, when we talked in class about being as accurate as possible. So if I round that up to 5%, I get 784.16 instead of 784.14. Those two are going to be close enough. Number 12. 10,000 is withdrawn from an account that pays 5% compounded quarterly for 8 years. What was the initial investment? Alright, so since it's compounded quarterly, we're going to have to use the formula A equals P times 1 plus R over N to the NT power. And we're gonna have to make the assumption here that if we're withdrawing 10,000, like we're closing the account. That's how much is in there altogether. So that's my final amount A. So 10,000 is equal to P times 1 plus my rate is 5%, which is 0.05. 0.05 over n, which is the number of times per year we compound it. If it's quarterly, it's 4 times, raised to the n, which is 4 times t, which is years, 8. So I've got 10,000 is equal to p times, I'm going to go ahead and calculate that, 1 plus 0.05 over 4, and I get 1.0125 to the 32nd. So I'm going to divide by 1.1025 to the 32nd. .0125 to the 32nd. So P is going to give me my initial investment, which is 10,000 divided by 1.0125 to the 32nd. And we get $6,719.84. Alright, 13. Half-life of radioactive actinium is 22 years. How much of a 6-gram sample will remain after 10 years? So the half-life formula from class is kind of like the compound interest formula, but we set it up as A equals, we'll call it P for principal. I don't want to do it that way. Let's call it this. We'll say Y is equal to A for initial amount times 1/2 raised to the years, say X over T, where T is the time to half-life, which in this case would be 22 years. X is the time that the time that's gone by, which would be 10 years. A would be the initial amount, which would be 6 grams. So Y equals 6 times 1/2 raised to the 10 over 22. So we put that in the calculator, 6 times 1/2 raised to the 10 out of 22, and we get 4.38 grams are left. Let's go to the right side, number 14. The population in thousands of Colorado Springs is given by P equals 361 e to the KT, where T is the year, T0 is 2000. In 1980, the population was 215,000. Find the value of K and use this result to predict the population of the year 2020. So let's see. So if 0 represents 2000, then 1980 would be a T value of -20 because we're going backwards. So this is my amount in 1980. So we're going to go 215. We don't need thousands because the population is already in thousands. So 215 is equal to 361 e to the k times -20. So we're going to divide both sides by 361. So 215 divided by 361 is, let's leave it as a fraction. 215 over 361 is equal to e to the -20k. Take the natural log of both sides. So the natural log of 215 over 361 is equal to -20k divided by -20. So k is going to be the natural log of 215 over 361 divided by -20. So k will be 0.0 0.0259. We're going to use this value, plug it back into our formula. To find what happens in 2020. So 2020 is going to represent t equals positive 20, because remember 0 was the year 2000. So P for the final population is equal to 361 E to the K, which is 0.0259 times positive 20 for years. Plug that into our calculator. 361 E to the 0.0259 times 20, and we get 60599, which we'll call 606. Remember, that's thousands, so that's 606,000 people. 15. Math Club is selling t-shirts to 450 members of the graduating class. The number of students wishing to purchase t-shirts can be represented by that model, where P is the number of price. P represents the price in dollars. How many students would want to buy the t-shirt if the price were $10? So again, P is the price, D is the number of people buying it, as in like demand. So we're going to plug in, that's our P value. So D equals 93 natural log of 32 minus 10. So D equals, that's just a calculator problem, 93 times the natural log of 32 minus 10, which is 287.46. 287.46 people doesn't exist. We're going to round down to just 287 people, about. What price would cause the demand to drop to only 50 students? So this time, that's D. So there's my formula. So this time 50 equals 93 times the natural log of 32 minus P. Divide both sides by 93. So 50 over 93 equals the natural log of 32 minus P. Exponentiate both sides. So I get E to the 50 over 93 equals 32 minus P. Subtract the 32. So E to the 50 over 93 minus 32 equals negative P. So we're going to have to divide both sides by negative 1. So that's going to make it 32 minus E to the 50 over 93 equals P. And we're going to go to our calculator for that final part. 32 minus E to the 50 over 93. And that's going to give me 30.288. So P would be about $30.29. All right, last problem, 16. The table below, created in 1996, shows a history of transit fares from 55 to 95, using the regression capabilities of your calculator to create an exponential model for the data. So, just like we did in class, we're going to create a spreadsheet first. So that's Control Doc for a new page. 4 for add a list and spreadsheet. We're going to give these variable names. I'm going to use year, but you can just use X and Y. Year and fare. And let's see, we've got 0, 5, 10, 15, 20, 25, 30, 35, and 40. And we've got 0.10, 0.15, 0.20, 0.3, 0.4, 0.6, 0.8. So there's my table. Now we're going to go Control Doc to create a new page. This time we're going to add a statistics page, where we press Tab. We want the X value to be years. Tab again to find the Y variable, and that's going to be our fare. There's my function that looks exponential. Menu, analyze our graph, regression, and we want to show the exponential function. And there it is. So we just copy that down. We can go out to 3 decimal places. It's probably good enough. So we've got Y equals 0.104. Let's go to one more. 1041 times 1.070 to the x. There's my function. Use the equation, determine the prediction that should have been made for the year 1998. So they told us that 95 is when our data stops, which is 40. So 1998 should be x equals 43. So I'm going to use my equation, 0.1041 times 1.0704 to the 43rd power. I'm going to go back to a calculator page. 0.1041 times 1.0704 to the 43rd, and that gives me 1.94. So that's $1.94. And then according to the model, in what year did the fare exceed $5? So that would be plugging in 5 for Y. So 5 equals 0.1041 times 1.0704 to the x. Gonna need a little bit more space here. So we're gonna divide 5 by 0.1041. 0.1041. You could also graph this and use the table to figure that out. I've got 48 equals 1.0704 to the x. I'm going to take log 1.0704 of both sides. So the year, or the number of years, is going to be log of 1.0704 to the 48th. I don't know, I just wrote 48. That should have been 48.03, be more accurate. So I've got log of 1.0704 and 48.03, which gives me 56.9, we'll call it 57 years. So with 40, just remember 40 was 1995, so 56 should be 16 years after that. So 1995 plus 16 should be 2011. So in 2011 will be when the fare exceeds $5. And that is the end of our review. Good luck on the test.